Hey everyone, welcome back. It's great to have all of you again and see you. I hope you had a wonderful week. I also hope that you have enjoyed your guided learning. You found it useful, and as well as the project. So today we are gonna officially kick off the second week, and we'll start with a project deep dive of week one. So I'm gonna start, and in terms of questions, we'll take questions at the end following the raise hands. So first, we'll just go over the project one deep dive. We'll go cell by cell and try to explain everything. So if you didn't get a chance to work on it, that's still fine because we are just going to go over everything and explain it. So I guess that's it. And one more thing before we start, project one was more like the entire week one was more focused on learning the foundations, like LLMs or how some of these things are working under the hood. And then similarly, the project was designed for that purpose. So the project has had to go a little bit lower level, just so we all get a sense of, what is tokenizer, how it's really built. When we talk about tokenizer, it's really just a list and things like that. But the starting project two, which is released today, you would see we'll focus less on the low level details and focus more on like application level and abstractions. So that was a note for project two, and we can start now. So project one was building an LLM playground, and there are two ways that we could run this. One was the Google Colab, which is freely available to us. It would also give free GPU, so we can load heavier models and play around with them. The other way that we could run and complete this project was to run it on a local environment. So the Colab is very straightforward. We just click on it and it would open on Google Colab. Then we can change the acceleration to GPU, and then we can just run the cells. It doesn't require any specific installations. Whereas if you want to run it locally, then you need to also install certain requirements, which we already provided a YAML file. So for this deep dive, I'm going to just run everything locally. So yeah, I'm sorry. I had to check a setting. So apologies. So yeah, we are going to focus on the local. Sorry. Give me 1 second. I have to change a setting to admit everyone. All right. So yeah, so the first step is importing all the libraries. So we have Torch, we have Transformers, and we have TikToken. Torch is more for basically it's Meta's framework for implementing neural network libraries. So a lot of the things that we've learned in the lecture, such as linear layers, convolution layers, and a lot of those, and already training and optimizations are already provided, and they are as part of the Torch library. So again, we don't need to go over all the details of Torch. It's a huge library, and it's not really, nobody is aware of every single detail about Torch. But we'll just focus on some key libraries and aspects of Torch. And then after that, we have Transformers. Transformers is basically the Hugging Face library. And then it's creating an abstraction so that we can easily load some pre-trained models. And then after that, we have TikToken. And TikToken is just OpenAI's tokenizer library. So we can simply use whatever tokenizers that they have trained and then just use them. So the first step here is to select my environment. So I've already installed using Conda. And then in the second project, we've provided the instructions for you to basically just use this Conda environment and install it, and then add it to your Jupyter notebook environment. But I've already went through those, so I'm just gonna select this here, LLM Playground. And now it's just starting my kernel. So now this is just for importing things. So here I've been able to import these libraries. And these are just the versions. I think the latest Torch version is 2.8, but it's fine. Still, we can use this 2.7. All right. So the first step was tokenization. Tokenization, we saw basically is a way to go from the raw text into the numbers. And then it's a process of converting this. And it has two phases. The first phase is to build it or train it using our training data. And then the second phase is to use it for inference. And here we are going to learn how to really build our tokenizer. And we'll try a couple of different tokenizations. The first step is a word-level tokenization, which we already saw. It works by splitting the sentence based on their white spaces. And this is just our corpus. This is a toy example. In practice, we don't have basically just 3 sentences. We have the entire internet data. So this is just an example. And obviously, if we work with this, we would have very limited number of tokens in the vocabulary. But again, in practice, there would be thousands of unique words. So here we have the pad and unknown. For pad and unknown, for now, we can just ignore them for a second, and we'll get back to this. Then we have vocabulary, word to ID, and ID to word. So these are some of the things that we are going to build. And just by just this vocabulary is going to be our tokenizer. This is what we are going to build. And it's going to be built from the corpus. All right, so let's see how to implement this. Basically, the simplest way to implement this is to go over all these sentences here. And then from each sentence, we split them by their white space and make sure that they are unique, meaning that there is no duplicate, and just add them to this word, to this vocabulary. So for doing this, let's start with first creating a set. And set is basically just something that's provided by Python. And it's just a collection of things. So it's very similar to list, except that it's a collection. There is no inherent order. And again, if you are interested, many of these can be searched online, like Python set. And then you would see like how it works and the data structure and some of the key methods like adding, popping, or things like that. So again, it's not expected to know all of this. So many of these can be just searched online. So this is where we create the set. And then now the next step is to go over all the docs like this for doc in corpus. And then here, now here, so let me comment everything here so we can keep printing it. All right, now if I print everything, it's nothing. Cool. So, so here I would just go over all the docs. For doc in corpus. If I print the doc, you would see the sentences here. The quick brown fox jumps over this. then tokenization converts text to numbers, and then basically it's 3 sentences that we had here. Now, what I need to do is now for each of these, I need to just split them by the white spaces. So next I would do like words equal doc dot split. And again, if you search a split, Python split, basically it's a way to divide a string based on some separator. So the separator can be anything. There is some default value. And then when you run it, you would see that the entire sentence is separated by those. So if I print now the words, we will see each word individually, which is fine, which is what we want. Basically, these are the individual tokens for word level tokenizer that we aim to get. Now, the next thing is the lowercase uppercase. For example, we have they here, we have another they here, and then this can be different from this just because the T is uppercase here and it's lowercase here. In word level tokenizer, it's very typical to just lowercase everything. So we don't make any difference between this day and this day. So this is what we are going to do. So that here, for example, we don't get this day and this day would become similar. So for that, it's very simple. We'll just need to use the lower dot split. So if I print this now, we'll see that everything is lowercase. And now we have every word ready. We can just add them to the set. So if I, so now basically if we go for W in words, we can just do word. Let me change this words. I would call this local words. And then here words.add W. Now, if I print these words, it basically keeps, it basically would keep adding all these words to the set. So here I print the words at the very end. Okay, for W in local words here, we add them to the words, and then here we print them. So here you would see we have this set with all those individual words. Now, this was a very simple step-by-step implementation, but in practice, we can also have everything in a compact version. So instead of having these 3 lines, we can just simply have, so here we can do basically, first we can, so let's do this. Let's, so this entire thing, and then we also needed to, if it's a function, we also need to return it here, but in this case, we don't. So now, instead of this entire thing, what we can do is we can simply write for doc in corpus, we do words.update. And then update is another method provided by Python for set. We can just keep adding new things. And then here for this doc, we would say doc.lower and then split it. So basically, this is going to be a list. And this entire thing would be just added. And it would update the words. So here, if I print the words, we would see the same list again. So, all right. So this is how we can build these words here. This is a simple form. This is a compact version of it. And next thing we want to do is now we want to form our vocabulary. So the reason that vocabulary, we have it separate as words is because in vocabulary, a lot of times we also add some special tokens. And what we mean by special tokens, these are some of the particular tokens that we would see 2 of them now, but in future weeks, we would see also more for reasoning capabilities and like end of sentence, like separating images from textual input and so on. But for now, we'll just have 2 very simple special tokens. One is pad, one is unknown. Pad, I'll get into it shortly. And unknown is basically, so I'll also get to that shortly. So keep these two special tokens for now. So to build the vocabulary, I have the words, and I have also the special tokens. So I can simply write here basically add and token, and these two is basically forming a list. And then I would add the words. So now if I print vocab here, I would see all the words as well as the special tokens. This was pad and on. Getting in the list, not set. All right. So it's complaining that words is not list. So I would just make this a list. So now we'll see all these special tokens as well as all the tokens that we extracted from our corpus. And everything right now is in a list. And that list is called vocab. So this is called the tokenizer. I mean, whenever people are talking about tokenizer or like companies release some trained tokenizers, it's just this vocabulary. And once we have this vocabulary, it's a list. So we see it here. So naturally, they come with indices. And the indices can be used to associate some IDs to these tokens. For example, pad is located in the very beginning of this list. So its ID is 0. Unknown is located next, so its ID is 1, and so on. So again, this vocabulary is all we needed to form our tokenizer from this very, very tiny corpus. Now, from this point forward, it's more for helpers so that we can easily use this tokenizer. We can basically create these dictionaries so that anytime we have a word, we can easily get its corresponding ID. And also when we have an ID, we can easily get its corresponding word. So how to build these vocabularies? It's also very simple. We can iterate over our vocabulary that we built. So again, here, if I print W, you would see all these words. And then here, I just need to, I also need their indices. So I can use the enumerate of vocab. And then here I can print basically I and W. And now we would see both indices and their words. And now we can fill these two. For word to ID, we can set word to ID of word equal ID. Then we can also say ID to word of ID equal word. And now if I print this word to ID, we should see the dictionary. So see, here is the dictionary. We have pad, its corresponding ID is 0. Then we have unknown, its corresponding ID is 1. Then we have fox, its corresponding ID is 2, and so on. And then in total, we have 20 unique tokens. And same for ID to word. Now, if I print ID to word, and let me remove this print. So now we'll see we can easily go from IDs to pad. So these are more helpers because now we need also write these functions to encode and decode any given sentence or any given sequence of IDs. So these two dictionaries can be very important to build. And again, in most tokenizations, when they are trained and provided, these three are already there. All right, so we have these things. Now the next thing is, okay, just a quick print here to see everything is fine. It says we have 21 words, and then these are the first 15 vocabularies. Now, the next thing is demo. Encode and decode. So let me uncomment these. So for encode, the purpose is to now go from this text into a sequence of IDs. So we have this word to ID, so that's going to be helpful to implement this. So all we need to do is now we need to go over all the words in this text and then extract their ID and return them in a list. So again, I'm going to first implement this step by step, and then we can make it in a compact version in just one line. So first we create these IDs, then we go over each word in the text. And again, we would lowercase it as before we saw and split it to get a sense, to get the word. Now, if I print each word, and then for testing, let me comment this still, and then print encode fox jumps. It's not gonna do anything at this point, but just print the fox and jumps based on this code. So we have fox and jumps. All right, so we are good. And now the next thing is now to extract their IDs now, and then append it to the list that we created here. So what we can do here is we can say IDs.append, and then for the word, we can say basically word. So we have this word, and then we need word to ID of word. Now this has issues. I'm gonna get to that in a second. But for now, let's just extract this ID and append it to IDs. And here we are gonna return all the IDs. Now, if I print this, return IDs. Now, if I print this, for this sentence, it should give me two IDs here, fox and jumps. Okay, so it's giving me 2 and 5, which makes sense. Fox, its ID is 0, 1, 2, and then jumps is 5. Now, all right, so we have this. Now, there is one issue. So for example, if we do fox jumps somewhere, there would be an error. And the reason for that is because there is no token called software, somewhere in our vocabulary. So it doesn't exist in this word to ID. And the typical way to handle this is now to create a special token, and we call it unknown. So basically, we create this and we put this here so that at inference time, whenever there is a sentence that it has a word or token which is not known to the vocabulary, to the tokenizer, it can be just replaced by this special token. And this is going to be very useful for both inference time and training, because even in training, after a while, we may come up with new data. And some of these new data may have tokens which were not previously used to train the tokenizer. So that's the purpose of unknown. Now, in this case, what we would do is we would say if word in word to ID, then we would say ID.append word to ID of word. Else, if it doesn't exist, we would simply IDs.append word to ID and our special token, unknown, which here is unknown, is this guy. So now we should have good IDs without any errors. So now if I run this, we should still get 2 and 5. And for somewhere, I would get the ID corresponding to the unknown token. So now if I print this, there are some errors. And so if word in word to ID, now I have to remove this 2. All right, so we get 2, 5, and 1. So 2 is fox, 5 is jumps, and then 1 is unknown. And that's because there was somewhere was not in the tokenizer. So this is the right way of implementing the encode. Now, this can be also implemented in a more compact form. So let me comment this, just if you're curious to see how the compact form would look like. So what we can do is we can do return, and then we'll get word to ID. So instead of extracting so before this, I'll do for W in text.lower.split. So at this point, we have W's, which are the lowercase individual words. So now here we need to get their ID. So we can do word to ID. Instead of doing like this, we can use Python's dictionary get method. So it returns the value if the key exists. Otherwise, it would return a default value, which is exactly what we want here. So here we can do W. And then if it doesn't exist, we would say word to ID of unknown. So now this code should also return the exact same sequence here. So let me run it. All right. So 2, 5, and 1. So this is how the encode works. And most state-of-the-art tokenizers are doing something very similar. They just encode the provided text by doing something like this. Of course, they have more arguments and parameters here, but at the very high level, this is how they're being implemented. So I'll keep this, but we'll move forward to, I'll remove this for testing, and then I'll move forward to decode. And decode is basically very similar, just the opposite of this. So I'm not going to go over it. Just the main difference is that now we are going from a sequence of IDs to an actual text or sentence. So we just need to do opposite of that. So how to implement that? I'll start with a, let's say, text. First, it's going to be empty. And then I'm going to go over all the IDs for ID in IDs. And I'll get the word. So first, I'll have a list of words here. I'll do just append, words.append. Now we'll go ID to word of ID. So this is good. And now we have all the words. So let me print it here. If I print words here, and then I do decode, I'm going to send the exact same sequence to see what happens. 2, 5, and 1. All right, so far we printed the words, and if you see the words, basically it's fox, jumps, and unknown, which is expected. Now we don't want a list. Decode basically is supposed to convert this sequence of IDs to just a string, a text. So we need a way to combine this. And the typical way to combine this is just using a join operation provided by Python. So we can do something like this. We can do a space dot join, and then we pass all these words. And then this can be our final text. So it turns out that we don't need this. And now here we can return the text. So here we see fox, jumps, unknown. And again, I write the compact form here. It's going to be return this dot join ID to word I for I in IDs. And then, so this should work, but also one thing that we can do is, remember we had another special token here called pad. We don't want to include those paddings. I'm going to go over the pad and why it's there, but for now, at least for decoding, we never want this special token to appear when we are going back from a sequence of IDs to the original sentence. So here we can do this and continue it by saying if I is not equal to word to ID of pad. So we just want to make sure that if it's not the pad token, then we're just going to use it to reconstruct the original sentence. Now, if I run this, I'll get fox, jumps, unknown. And then if we have at any point the ID corresponding to pad, and let's say another here, we would still get the fox, jumps, unknown. So we are good on encode and decode, and this part is now complete. I can remove this, we can uncomment this, and we can run it. So we'll see, if we have 21 words, we have all these unique tokens, and then we have basically the input text, which is the brown unicorn jumps, and then we have token IDs, which are the corresponding tokens. Now, one thing to note here is that we have unicorn, and unicorn was not part of the our vocabulary, so it got replaced by unknown when it's decoded. And that's typically a problem. Ideally, we don't want to see too many unknowns because it's just losing the information for model to learn from. So For example, for the brown unicorn jumps, if we don't have unicorn in our vocabulary, anytime we are going to train on sentences with the word unicorn, it would get replaced with unknowns. Now, if there are a lot of unknowns, the LLM would get confused and cannot learn really the statistics and the pattern between these words. So this is not ideal, but it's the best tool we have to make sure that at least at inference time, the decoder is not going to fail. It's just going to replace it by unknown. And again, we can also modify this implementation to make sure that if something is unknown, it won't print it. So we can just continue adding this if I not equal this and I not equal the unknown token. So that's it for this section of word level tokenizer. So we just created this vocabulary, and that's all we needed to do. First, we needed to decide on our special tokens. And in this case, we had two special tokens, unknown and pad. And then we just built it. We just used our entire training data. We created the words. And then from the words, we built our vocabulary. And then once we had the vocabulary, the rest was just helper functions to make sure that we can encode and decode. So that's it. Now we are going to go to the next part, which is the character level tokenization. And at its very core, it's very similar to word level tokenizer. Now, one issue that we observed here is that each word is going to get its unique ID. So there would be a lot of unique words in our vocabulary. And that's not ideal, especially if you are training on internet data and lots of different languages. This may become like hundreds of thousands of vocabularies. So that's not efficient. And also, if we train on internet data, still there is going to be a lot of unique words that were not in our tokenizer. So we may end up with a lot of these unknown tokens during training, which is also not ideal. So character level tokenizer, it's going to be similar. What we need to do, again, let me comment here. And then we start here and we form them. We already have the corpus. The corpus is the same. This is our corpus. We just now need to run character level tokenizer, meaning that we want to split this based on each character, and each character would have its own ID. And we also need to make sure that it's a set, meaning that there is no duplicates. So let's just start implementing this. Again, I'm going to create these letters first. I mean, there are different ways this can be implemented. One is we can simply write A, B, C, D. If it's English only, A, B, C, D, E, F, G, H, I, and the rest. The other way we can do this is we can rely on this string library provided by Python, and we can just do like a string dot ASCII lowercase. So this should, I believe, this should give us all the lowercase characters in English. Now, if I print this, we would get A, B, C, D, and all the way to Z. We can also get uppercase. So we can, if we do a string dot ASCII uppercase, now we would get all the letters, all the English letters. And again, this is a very simple example. In practice, even for word level tokenizers, you may want to go over all your corpus and do something very similar that we did here, just split them character by character and form your unique vocabulary. But here, I'm just going to use these lowercase, uppercase letters from a string. And again, we're going to have our special characters. I call them special here, and then pad unknown. So these are our special characters. Now, vocabulary is going to be these two. I just need to make this a list. Now, if I print it, I would get a list of all basically the unique English characters as our vocabulary. Again, there are different ways. It depends on the design. We can always start from our corpus and build our unique characters. if there are multiple languages, or we want to include like numbers and exclamation points, question marks, and all those things. But for now, we'll just intentionally gonna keep it simple and just use English letters. So now we have this vocabulary and we are good. We no longer need this. Now for character to ID and ID to character, it's very similar to what we saw before. For car to ID, we have this. So again, I'm going to use the compact form. I'm going to do like, first it's a dictionary, and I'm going to do for IDX and characters in all the letters in our vocab. And then here I'm going to say your key would be, because it's char to ID. So the keys are characters and the IDs are the IDs, like where they are located in this vocabulary. So we have character here, and then the value would be the IDX. Now, if I print this char to ID, all right, it's basically giving me, okay, this is a special token. It's a different story. But the rest for each character, now we are getting their corresponding ID. And then in total, I think we should have 53 plus 1, 54 tokens. And that's because we have all the English letters and 2 special tokens. So this is good. Next, we want ID to char. And for ID to char, there are 2 different ways we can do it. We can either, again, go over the vocabulary, or we can just go over this char to ID that we just built. So I'm going to go over this char to ID for CH and IDX in char to ID.items. So this would give me like the items over a dictionary would give me the pairs of key values. So which in this case for character to ID, we have character and the index. So for all of these, now we just need to swap this because now we are going from ID to character. So we have IDX and so here we have IDX and CH. So I think this should work, hopefully. Print ID to char. All right, so we'll get 0, pad 1, unknown, and so on. So we have these 2 now, and let me just remove this. And these are working. Now, if I uncomment this and I run it, I'll get the vocabulary size, 54 expected. Now, encode, decode. Let's start with encode first. So here, again, we are given the text. We just need to iterate over the text and just retrieve its ID and return it. So for that, I'll do, again, the compact form, return a sequence of this for CH in text for each character. We have char to ID. So we can just say char to ID of CH, but this is not ideal because we want to also handle the unknowns. So here I'll do get, and then here I would say get CH. Get CH. If it doesn't exist, I want the unknown. And for unknown, we have char to ID of unknown. So I guess this should work now. So if I print encode hi, hey, how are you? And I print it. All right, we'll get an error here. Name char to D is not defined, so there is some misspelling. Now unknown is not defined. Okay, so now I have everything for like a sequence of IDs for this given sentence. So basically now we are able to encode this. We build a token, character level tokenizer here, and also we created this. So now we provide this functionality. In encode, anybody can just use my encode function, pass whatever sentence they want, and they'll get for this sentence a sequence of IDs. And again, if you watch the guided learning, you see that now we are getting a very longer sequence compared to word level tokenizers, just because now for each character, we have a separate token. And this is not also ideal, because now the LLM should look at all of these and learn the patterns among all these very long sequences. So it's not efficient and it's more difficult. But again, this is the encode and how it's typically implemented. Now let's go to the decode. So decode is kind of just the opposite of that. If we do return, so here we don't need to join by a space because we did not split. It's not a word level tokenizer. We didn't split by the white space. We just went character by character. So we just need to add them all. So I'll do just an empty string dot join. Now, what do we need to join? Just a list of corresponding characters given these IDs. So we go over all these IDs for I in IDs. And we make sure that if I is not equal to char2 ID of path, I'll get to this path in a second. And then if that's the case for all these for I in IDs, if I is not this, so here we need their character, their corresponding character, ID to char of I. And now we are joining them all. So now if I do print decode and pass a sequence of IDs like this one. So for this one, we already know what the output should be, what the reconstructed sentence should be. If I print this, I should get, hi, how are you? Hi, how are you? All right, so here there is a problem because for all the spaces, we are getting this unknown. And that's because when we built our tokenizer, we didn't have any special token or any tokens for a space. So this can be also handled in different ways. We can perhaps add a space here to our vocabulary or to our letters, just to make sure this can also be handled and rerun this. When we rerun this, we are basically rebuilding our tokenizer vocabulary and all these dictionaries. So now for this sentence, let's see if we get okay, so first I have to encode it again. Print encode, hi, how are you? And notice that here now I'm including all these white spaces. Let me also add a question mark here, but question mark is not part of our vocabulary. So it's going to be replaced by unknown. So if I print this, we'll get this sequence of IDs. Now, if I replace this here for decoding, now I should get the original sentence back. Hi, how are you? But again, the question mark is now replaced by unknown. So that's about character level tokenizer. And then let me uncomment this part. Again, these are once implemented are generally very easy. Again, the purpose is just to show that it's not like tokenizer is just a list and a vocabulary. It's nothing more. So let me now run this. So we have hello, we have its corresponding token IDs, the sequence of characters, and then the decoding is also hello. So that's working. Now we'll switch to subword level tokenization. And also we mentioned in the guided learning, word level tokenizer and character level tokenizer are not really used in practice. They are having their own issues. We went through those. And in practice, most of the state-of-the-art LLMs are relying on subword level tokenizers. And there are different algorithms, like a common one is BPE, byte pair encoding, or some variations of it. And there are some other implementations or different ways of subword level tokenizer. And the main idea behind it is to start from very small bytes or characters, and then iteratively merge the most frequent pairs. So it basically starts from every character and it becomes its own token. And then it would count the most frequent pairs in the corpus. And if there are pairs that are very frequent, it would just merge them and create new token in the vocabulary. So it just iteratively increases the size of the vocabulary. And that's how many tokenizers get into like 50K or 100K tokens. So I guess I have this tick tokenizer here. So here there are a bunch of tokenizers provided by and trained by OpenAI. And this one is, for example, the one with 100K tokens. And I believe they are using the variations of BPE. If you go to the tick token library, we would see like each model was trained with which tokenizer. And then the more recent one is 200K. So they're having 200 tokens after they are training their vocabulary, their tokenizer. So their vocabulary list has 200K items. So hi, how are you? We'll get into this. So we'll get into this very shortly. I just wanted to show the tokenizers and how it's different. It's not really splitting this based on words. It's splitting this based on the created and merged tokens that it was trained on or it was learned during the training. So we'll get into this in a second. All right. So subword level tokenizer is after it follows this algorithm, the good thing is that for less frequent words or unusual words, they won't end up with their own token. For example, unbelievable would become something like this, like a smaller set of characters which are more popular or common in English. And that's how it's not decided by us. This is just decided by the corpus and the algorithm. The algorithm would just go over the corpus and come up with most frequent like subwords in the training data. And this is just an example. I don't know if for unbelievable, yeah. So unbelievable, for example, in BPE, in OpenAI's O200K base tokenizer, it gets divided into 3 different tokens, UN, BEL, and EVable. So and one more interesting thing, for example, if I write, hi, how are you? Each of these meaningful, very frequent words are becoming 1 token, which is great. Now, if I have a misspelling here, like how with double O, the algorithm, the tokenizer, would just know that this how is 1 token, and this is just becomes in just its own separate token. So instead of turning this entire thing into unknown, it's extracting the meaningful part to a token, which is awesome because now LLM can see this how, even though there was some like mistakes or misspells here. And then W, which is just a pure noise, would appear here, which the LLM is just need to learn to ignore some of the tokens if they are irrelevant in sequences. But just showing this example to say that what are some benefits of this subword level tokenizer. Now, going back here, for BPE, there are lots of different implementations available, and the implementation is usually requires more lower level coding. And basically, you just need to follow these 3-4 steps. But we don't have to because there are libraries that are already implemented those and made those available to us. So one of those libraries is we can just easily rely on the so transformers. I mentioned that it's the Hugging Face library, and it give you access to open source models. And as a result, since you have access to open source models, you also have access to their open source tokenizers that were used to train them. And very simply, we can just import this auto tokenizer, and then we can specify the model that we want its corresponding tokenizer. So this way, we are going to just load GPT-2. So we can have something like BPE token or tokenizer, and then do equal auto tokenizer dot from pre-trained. Here we can just write a model. And if you are interested, I think Hugging Face auto tokenizer models or something like that, I think it would just give you a list of all the available models. So I'll try to find this. But basically, there is a page where it just shows all the models that you can easily get their model or get their tokenizer. I think it's not. Yep. I'm going to share it, but basically it's like this. For any tokenizer, we can just do auto tokenizer dot from pre-train and then just pass a reference to the model that we want. In this case, it's a vision language model, but it could be any LLM or any pre-trained model. So we'll just here gonna use the GPT-2. Now, again, let me comment everything and then say print BPE token. It would just auto tokenizer is not defined. All right, there was a misspelling. So when we load it, we get this entire tokenizer object used for GPT-2. And you can see it here if we print it. It says the vocabulary size was 50,000 something. This is the max length, padding size, and so on. Oh, by the way, I forget to say the pad. So the pad is there as a special token because when we train LLMs, we don't typically send one example. We send a batch of examples because sending one example is not it's not efficient. It has also some other issues. So we typically batch them, send just put multiple examples and just send them as a one input to our model during training. And these models, LLMs or most neural networks, require fixed dimensions as their input. So if we have multiple sentences with different length, it would not just work because when we convert them to a sequence of IDs, we would end up with sequence of IDs with different length. So the purpose of pad is just to pad the smaller sequences to with these special tokens, just to make sure that each time we send a batch of examples, they have a fixed length. So that's the main purpose. And then during training, the model would just ignore this path. So going back here, so this is what we see here. So it's saying that the model was trained on sequences of length 1000. And then whenever there were some examples in their input where the length was less than 1000, it was just being padded. And it was padded from the right side. So these are some of the design decisions. And here you would see the special tokens are beginning of sentence token, and this is how they represent it. End of sentence token, and this is how it's represent the special token, and unknown. So GPT-2 had three special tokens. Our very tiny tokenizers we built above had two special tokens. So that's it. Moving forward, it would be faster because now we are just relying on this tokenizer. We don't have to really go and build vocabulary and things like that. We can just write the code. And they already come with the encode. So I included this part just to be consistent with the previous implementations. So we can just have bpe dot underline toke, the object that we created, and then we call their encode. They also come with encode and decode, very similar to how we implemented our tokenizer. So we do encode and then we send text. So that should be it. Now we can easily encode anything. Print encode hi, this is Ali. And then we'll get this sequence of IDs. So hi has this ID, this has this ID, and so on. Let me also remove this print and remove this. And now we have this encode ready. Now for decode, it's again very simple. bpe.toke.decode of IDs. So decode of this sequence should give the exact same. Hi, this is Ali. Now, the good thing here is that we can now use some more special characters, and the tokenizer, the BPE tokenizer, would be still able to decode it and encode it. And this is what we had in the demo. Now, if I print this, we would see the input text unbelievable tokenization powers is getting these tokens, UN, Bell, Eve, Ebel. So these are some of the tokens that were decided by the BP algorithm when they trained their tokenizer for GPT-2. So if we use a different tokenizer, it may end up with a different sequence of IDs. So if I copy paste here, copy paste this in tick tokenizer and use the O200K. So here they have Evable as one token, while their older version had two tokens, Eve and Able. Again, it all depends on their training data. Another thing is it handles certain characters the way it wants. For example, it also converts each byte to a printable format. So that's why we see this very special character here. It's basically in the very beginning, when they are building their tokenizer, they go over all the bytes corresponding to the ASCII characters, and then they come up with a mapping. So they go from that to a printable Unicode character so that they can just print it. And that's the only purpose. So that's why here we have this space token is having its own token, its own ID in the vocabulary. And then for printing, basically this space is mapped to this particular Unicode character. So that's why we see this. And the rest are normal ones. And then here again, we have something. Exclamation point has its own token, and so on and so forth. And emojis are being split into multiple tokens. Again, we don't have to know how they are split. This is just decided by the way it's trained and the training data. So here, if I just paste this, okay, this emoji is basically two IDs. So whenever you send these two IDs to a LLM, it would just, over time, it would just learn that this might correspond to, like in their meaning, something to this emoji. So that's BPE. We can just play around with different methods, different texts later if you are interested. But that's how we can use BPE and train our own model. And finally, I want to talk quickly about TikToken, which is a production ready library. So this is just provided by OpenAI, and it just gives you all you want from different models. It's very simple to use. I don't know their particular methods. So if we go to their library, TikToken library, this is their Git repo. And then you would see this is how it can be used, imported, and get encoding of a certain tokenizer that you want. You can also get the encoding of a certain model that if you are interested. So this is how you get the encoding, and then enc is basically your tokenizer. You can just start encoding and decoding text. See enc dot encode hello world. So we'll do something very similar here. Now, I'm going to just implement this very fast for name. And so we want to try two different examples. So we have encodings equal a list of two models. First, we are interested in trying GPT-2. And then we'll say, all right, GPT-2 TikToken.get encoding GPT-2. And then the other one that I'm interested to try is, let me just copy paste this, and same thing, TikToken.get encoding this. So now we have encodings, we have what is all right. So now we have encodings. If I print encodings, I would get just this list of pairs. Now I'll do for name and ink in encodings. Let's just print the name and vocabulary size. So for this, I can do something like this, and then name and this, and then print vocabulary size, this, and then ink.n vocab. And then we'll encode some sample sentence we have there. So we'll do IDs equal enc.encode sentence. Let me print IDs to see if it's working. All right, the IDs are working. Then I would say tokens equal end.decode of I for I in IDs. So here we are getting all the tokens. And now it's time to print everything. We can say sentence sentence splits into len of IDs just to see what is the length of the tokens for that sentence. And then I'm going to print here list of zip of tokens and IDs, because tokens are their words and the IDs are the like a list of IDs. So for each of those, I'm going over them and just printing their list. So what it's saying is that tokens encode for I in IDs. All right, decode is a method. All right, so for GPT-2, vocabulary size is 50,000. These are the 11 tokens, and then these are the pairs of all the tokens. And then for the more advanced tokenizer, we have 100,000, and then we have all the splits and tokens. So that's it. And then the opposite we can do, we can just change this to decode and just print it. So that's the tokenizer. Next, we are going to go to the language model. Again, in the lecture, we've seen that everything is basically just a sequence of layers. And I have the lecture open here for simplicity in implementation. So linear layer is basically just these weights. So we need to have a Python class and keep these weights, create these weights, initialize them with random values and keep them. And the size of these weights depends on size of the inputs and size of the output. So a lot of times when we want to create a linear layer, we have to specify this is the expected input size and output size so that we can internally create and initialize its weights. And you can see, for example, here we have four input size of size 4, and then the output size of size whatever. So the number of the matrix for weights is basically this times this. And we are going to implement this by our own, just to get a sense of how linear layer can be implemented. But we never need to implement this. It's just for us to get a sense of it's not a big deal. It's just a few lines of code. In practice, we just use on Torch's linear layer, which is called nn.linear. But here we want to implement our own linear. So let's see. So here first, let's let's create a layer, linear equal linear. Let's a simple example, 3 by 4. So 3 is the input features, 4 is the output features. And then here, let's just print it. Print it. So for now, I think it's not gonna print anything because we haven't implemented. But now what we need to do is there are basically in the initialization, we just need to do two things. One is we create the weights, which is this matrix. And also linear layer has a bias term. So for each term, it would add it to the bias. The size of bias is equal to the number of outputs because each of these terms after the matrix multiplication, the bias term would just be added. So just to get a sense of the dimensions. So here, first we can create some random inputs. Let's call them weights equal. Torch has various methods. Rand-n is basically creating a random tensor. So if I say random tensor of out features, number of output features and in features, and then we write self.weight, just linear.weights. It would now give us a random tensor of torch.rand-n. All right. So this is the random input that we created here. These are the initial weights. These are basically what we initially gonna assign to each of these edges, but later during training, they will get updated. So that's about weight, very simple. And now we need to just make sure that they are parameters. They are not just some random numbers. So we'll use nn.parameter to make sure that these weights are trainable during training. And self.bias, again, it's all about the dimension to make sure we are right. So it's going to be torch.randn out features. So now we have these two weights of the linear layer. Now we just need to implement the forward. The forward is basically it's just the terminology that PyTorch uses. It's basically specifying how the transformation should happen. Now, given some input X, how is it supposed to be transformed? So here we go from this input to output, and this is a linear transformation. So we just need to implement that kind of linear transformation, which is a matrix multiplication. But again, this is where we implement like how the transformation should happen for different layers. In this case, it's very simple. It's just a matrix multiplication, and Torch already provides that. We do matmul. And then input is X. We just need to perform a matrix multiplication of that and the weights. So for the weight, I have to transpose it by calling this T because it's out.in. We need in.out times out. So we'll do this, and then we'll just add everything with self.bias. Now that's it. Now we have this linear. We have the weights. Now if I create some random input, torch.rand one of like 3, and I just pass this 1 by 3 is basically this guy. I'm creating this just randomly, and then I'm gonna send it to this linear layer, and the output we're gonna inspect it. So I'll send this X to the linear layer, and then we're gonna print Y. Now Y is expected to be of size 1 by 4 because here we have specified 4 when we created this. So now if I run this, linear object has no attribute weight. Misspelling here, weights. All right, we are just getting the output, just 4 numbers. So that's how linear layer is implemented in practice, but we don't have to implement it, never. It just gives us, Torch gives us this functionality. So we can just import torch.nn, which contains all the different implementations of different layers, including linear, and then simply call nn.linear. And then here we specify the sizes. In this case, again, is 3 by 2. And then we create a tensor, a random tensor here, just to see if it looks right. And we can just run it. So it's basically the equivalent of what we just implemented here. And again, transformer is just a sequence of layers, linear layer, MLP layers, attention layers, and attention by itself has also a sequence of linear, a couple of different linear layers. So it's nothing special. It's just a sequence of layers, and you can just print them. Now, we are not gonna really implement any of those because, again, transformers give us access to load these models and inspect them. And this is what we are gonna do here. So here we are gonna load GPT-2 and inspect it. I'm gonna write GPT-2 equal GPT-2 LM head model dot from pre-trained. And then I write GPT-2 here. So now if I run this, it would give me the GPT-2 model. Now I can inspect it. If I print GPT-2, we would see all the layers when it was created. It has a transformer layer. This is the module name. It has the position embedding and the word embeddings. And then it has also a sequence of modules, which is the transformer blocks. Now it has 12 blocks. Each block has layer norm, attention, and another layer norm, and MLP. And MLP is just, again, by itself, a sequence of layers, convolution, some kind of nonlinear activation and dropout. Very simply, you can inspect other models, more recent advanced models, to see how they look like. But we are not going to do that for now. We are going to stick to just, let's see, a block of the GPT-2. So block equal GPT-2 dot transformer, which is here, and then dot h, which is this module list, first block. So now if I print this block, it would give me the first block of the transformer. It is one block of this. And you can see it has attention, linear transformation, and MLP. So it's basically the attention, and it's decoder only. So it's attention and then feed-forward layer. So that's the block. And then after this, we can just print some modules just to get a sense of everything inside it. We already saw, but just to show a more systematic way of printing this is to go over all the children of this block and just print them. Print name and module dot class dot name. I guess it should be something like this. So it has these names and these classes. Each block has a layer norm GPT-2 attention, layer norm GPT-2 MLP, which exactly follows this setup. All right, so we'll go here, just a tiny example, just to see how it works. We already have GPT-2. We can already access to its configs when it was trained. Let me print the config here, GPT-2.config. So these are the configs that were used to train GPT-2. So you can see like what activation function is being used there, the probability of drop for attention, different token IDs, and a bunch of other things. And basically the precision of the tensors that they're trained on, vocabulary size, 50,000, we already saw it, and so on. So that's GPT-2. We can get the vocabulary size and create some dummy random tokens as input. Just we want to test it and pass it through the GPT-2 and get some output. So here we are just assuming a sequence length of 8. So what this 8 means is eight numbers. Basically, we want to generate 8 numbers here and pass it to GPT-2. And for now, we are just going to generate these random numbers. And it's important to make sure that these numbers are within the vocabulary size. So we don't want any of these numbers to be outside of the vocabulary. So that's why we set this, just to say that all these numbers should be within the range. And then here we set the size of these dummy tokens. We are saying that it's just one example, and we want 8 tokens. So now if I print this dummy tokens, and comment this, we'll see this randomly generated IDs. So that's about it. Now we just need to pass it to the GPT. And there are different ways. I mean, first I would just convert each of these dummy tokens to their embedding. So this is this step, to go from these tokens to these vectors. This is called embedding layer. And embedding layer in GPT-2 is, let me delete this cell, we printed GPT-2. It's basically called WTE if you print it. So WTE is what it's called. And then here we can just simply pass our dummy tokens, a sequence of numbers, to get a sequence of vectors. And now we need to also add this with the positional encoding. Positional encoding also converts each tokens and incorporate the position information. And then those are being added to form the input. This is the input. This visual is not showing the positional encoding, but we typically add the position information and add them to each token. So this plus GPT-2 dot transformer dot WPE, they call it. And then here we just need to pass, we don't need to pass the tensors anymore. We just need the locations. So we want the locations to be added. So we use a range of sequence length. So now this is forming our input or hidden based on the dummy tokens that we've created. And once we have this, we can now pass it to the first block of the transformer and see what happens. So we pass this hidden to this, and then we see if it works or not. Out, and then here we then print the shape of the out. So what we expect is that the shape should be the same size. We created one example of sequence length. The output should be one example of sequence length, but also includes the hidden size, because the output here is of same sequence length, but has this hidden dimension, which is the same as this hidden dimension. So basically, we are just passing this to one block of transformer to get this output. And we are going to print the shape of this output. So here, if we print this, we'll get the shape of 18768, which is correct. 768 was the hidden dimension of GPT-2. 8 was the sequence length. And 1 is just because we created one example. So that's it. Then the next one is, I'm going to skip this because we already printed and saw all different modules. And then finally, we'll go over here. Now we want to pass this and get the logits. So for this one, I have the code here. I'm going to copy paste. It's very simple. We already went through most of them. First we load them. We have already GPT-2. If it's not loaded, we say, hey, load it from this pre-trained GPT-2. Also load the tokenizer. So first we load them. Then we tokenize this input text. And it's just one line of code here. We pass this text to the tokenizer. We already saw it. And then we get the input IDs. So if we print this input IDs now, print input IDs, and I comment everything else, we'll get the IDs corresponding to hello, my name. So basically in this example, I want to pass this hello, my name to GPT-2 and see if we can actually get the next token. So that's what we are trying to do. All right, so we have these tokens now. Now we need to pass this sequence of tokens to the GPT and get their output hidden vectors. And this is, again, like 2 lines of code. We just do no grad because we are at inference time. We don't want to calculate the gradients. And we write logits. So we pass the input IDs, sequence of IDs to GPT-2, and then we get their logits. So now if we print the shape of these logits, we should not be surprised. It's 1 because it's one example. The 3 is basically 3 tokens. And then this is basically the final output. So it's not this. It's after applying linear. So it's mapping this entire thing to the right dimension for over the entire sequence of vocabulary that we have. So that's why we have this size here. Oh, actually, we had this print already. So now how can we predict the next token? We saw that all we need to do, we have these logits, and these logits are good. We just need to keep the last one and then apply a softmax to convert them to vocabulary and just print it. So this is the code. We have the logits. We get the first example because it's just, we have only one example. We get this. Then we get the last hidden vector. So there are 3 hidden vectors. We index the last one. So this basically means that we are only keeping the vector, the output of linear for this, the mapping of this. We are just discarding all of this. So we get this next token probabilities, but it's logits. Now we need to apply the softmax to convert them into vocabulary, into probabilities. So here we would get a list of vocabularies of vocab size, 50,000 something. And now we won't print it because it's just a lot of numbers. We would get the top K. Torch has also this top K. So we can just say, hey, give us the top K probabilities, and specify the K here. So here, if I print top K, it comes with two values. Yes. So values dot to list. So let's see what GPT-2 thinks that the top 5 probabilities would be. Okay. All right, it's just outputting the top probabilities. The first probability is 77%, so GPT-2 seems confident about the next word, and the rest is very low. So now all we need to do is just we need to print their corresponding tokens. So I'm gonna print this here. Now for the top 5, we go over all the indices and the values, and then for the top value, we pass it to the tokenizer because they're just IDs. We pass them to the tokenizer decode to get their corresponding token. Now, if I print this, we would see the highest probability word is with 77%. And that was expected because the input was hello, my name. If we change it to like hello, then the network, the GPT-2 would be less confident about the next word. Somehow it crashed. So let me quickly rerun. All right, so I think we can pass this. It's gonna run, and then we saw that for hello, my name, the next token is. Now the next thing is we go to the generation. For generation, I mean, from this point forward, it's going to be much, much faster because we just learned the high-level ideas, and I'm just gonna copy the code and go over them. So we learned about greedy decoding. So we can easily load models, let's say GPT-2, their tokenizer and model. And then Hugging Face also provides a way to generate. So we don't have to really implement all those things that we implemented here, getting the logits and getting the last one, applying softmax, top K, and anything. We can just ask Hugging Face and pass the parameters, and then it would generate for us. So here, let me copy paste this. All right, this is going to be super simple. We are not doing anything fancy. So we have just a list of models. It's just one example here. We are loading them, tokenizer and model we saw earlier. Here we make sure that this particular model has already a path token. If not, we just set it. It's just unnecessary detail. We don't have to worry about this. And then here we build our dictionary of tokenizers and models. In this case, we are just having one example. So, and then we generate. So for generate, again, it's a function. It comes with a model key, prompt, and a strategy. And we don't have to implement this. We just tune the parameters that the Hugging Face expects. So if we search Hugging Face LLM generate, you would see text generation and how it works and what are the expected inputs. So here it's basically saying that these are model inputs, and you can take a look at the different inputs that Hugging Face expects, and also beam search if we want this to be sampled or greedy, like deterministic and so on. So you can just read this at your own convenience. But here we have this generate, and we just update these flags. We get the tokenizers and model, then we generate these arguments. So we send this sequence of tokens. We specify based on what the input strategy is. If it's greedy, we say don't sample, it's false. If it's top K, we say sample true, and we provide top K and temperature values. And same for top P. And then we ask it to generate. We just use the generate method provided by the Hugging Face model since we loaded. And if I run this, it says loaded GPT-2, and then it already has this generate. So if I run this now, so it would run if you run this on Google Colab. I guess for my Mac, I have to change it to use my accelerations. So here I run this again, it loads GPT-2. I run this again. It's basically generating. So for this sentence, it started to generate. And then here, the continuation is like this. Once upon a time, the world was a place of great beauty and great danger, and so on. So basically just continuing my sentence. And some more examples, I would share this notebook anyway after this session, so you can go over the outputs. And same goes for different strategies. So if I rerun this with top K and top P, we would perhaps see better and better outputs. Now, finally, the last part is the last part is now we want to switch to better models and perhaps like chat completion. So far, we see GPT-2, and it's just a continuation. We want to see also the completion model, so we can actually ask questions. And the code is not really different from what we saw. I'm gonna copy paste from here. Again, tokenizers, model, we set the device, and then we go over them and run it. Now, this was the default. It's gonna run on Colab. It's not gonna run on my MacBook. I'm not gonna try it. I know it's gonna crash. So instead, there are these two models that have previously loaded, Qwen 3, 0.6 billion, and Gemma 3, 270 million. And then these would work. And again, you can see a list of Hugging Face models. If you just search like Hugging Face Qwen, you would see all different Qwen models here in the model card. So if you click here, you would see all different models with different number of parameters. We have 8 billion, we have 0.6, instruct, 30 billion, like everything. Like instruct are the ones that are for chats. But again, I just try to pick these two, and they're relatively new. Gemma is Google's Gemma 3, 270 million. It's extremely good and efficient. And same for Qwen. And this one, you can also run it on Colab. So let me run this and see what the output might be. So loaded GPT-2. I hope it doesn't crash because there are 3 models now. All right, so 1 model, 2 model was loaded. 3rd one was also loaded. So now if I run this on, let's just do 1 on Qwen, it would use the Qwen model and sample from it. I can also change it to Gemma to see what is the difference and what Gemma would produce. It's going to take longer because some of these models are now bigger. But all right, so it created. Once upon a time, there were 3,000 people in a town. So later, if you compare this, you would see that the quality is typically better and higher compared to GPT-2. Okay, we're almost done. And let's see, I think there is one more step. All right, so it just ran Qwen. Again, I'm using Qwen 3. It's not a chat model. You can use this chat model in the Google Colab, or if you have a more powerful laptop or GPUs, it's not just going to run on my laptop. And if we change this to Gemma now, it would use Gemma to sample from these using these 3 examples. I'm not going to run it. So that's mostly it. The last part is just an LLM playground. That's not the focus of this course or this project. It's just a UI implementation to just get a good feeling of how it looks. I have something to copy paste here. It is the simplest UI possible. But let me run it, and also let me make sure that we are using the GPT-2 and Gemma, which is already loaded. All right, this is my UI, and it's again, I'm going to share this code so you would have access to the code, but it's the most simple UI you can think of. And then we can choose GPT-2 and Gemma 3 and the strategy here, and you can also set the temperature. So let's try GPT-2 and tell me a joke, and we can press this generate. So again, this is a continuation, like it's a completion. It's not a chat model. So it's just continuing. Tell me a joke about it. I'm not sure if you are aware of it, but I'm not sure if you are aware of it. This is one of the typical issues of GPT-2, which we covered in the guided learning. It just gets stuck in a loop. If we change the strategy, I don't know if it's going to make any difference in this particular case, but let's see. All right, it's better. At least it's not in a loop. It says, tell me a joke. I thought you'd have to get some help. So it's basically repeating or generating what it has been seen in its training data from internet. Now, if I change this to Gemma, it's still the same because it's not a chat model, but it might the output might sound more meaningful. I really don't know if it's working on. Okay, it's working under the hood. Tell me a joke, but don't laugh. I could hear the voice saying, don't, you are the most best person I've ever met," and so on. So feel free to play around with it with the temperature to see how when you decrease the temperature, the results are more expected and deterministic. And when you increase the temperature, you would see more creativity. And sometimes if it's too high, the results would not just simply make sense. So, all right. So we covered everything. I'll just keep the code and we'll push it. Next we're gonna take some questions from raise hands. But before that, I want to quickly share that we have released the project and also the material for week 2. Week 2 is going to focus on the RAG. So let me quickly show this and then we'll take questions. Here. So week 2 is already available. The video has now captions and also it has the chapters for convenience. Also, project 2 I try to improve project 2 based on all the feedbacks that we've received for project 1. So it's also focused on RAG. It's less high level, it's less low level, it's more high level. And also it has a lot of links for you to go over and take a look and more comment for libraries. So you understand the purpose of each library. And also it comes with some hints, like 2 lines of code, and so you get an idea of how much lines of code it's expected. It also comes with a bunch of other things. So expected steps, so you know how to implement it. What are the steps? You can just follow this. So if you have any feedback for project 2, please also let us know. We can improve the project 3. So let's go to the questions now. I'll start with Peter.
Hey, first of all, I really appreciate the depth of what you've gone over so far, but I'm wondering, I have a question about the input size and the output size. In your presentation, you had this diagram. If you can pull it up, I might be able to point you to it, but it's like you have 4 input neurons and 8 output neurons. And I just want to understand what your point is that you were making when you were saying that you have these 4 inputs and these 4 outputs. Could it be 4 inputs and 2 outputs or 3 outputs?
Yes, basically you can decide any number of inputs and outputs, and it depends on your design and the neural network that you are implementing. But this needs to be fixed. This needs to be decided ahead of time, right? Because it cannot be adjusted, because the weight size needs to be determined and fixed when we are building the neural network. So all we need to. Go
And this
ahead.
is something that's very complicated and has to do with the structure of the neural network itself. It's not something that we could just decide arbitrarily.
Of course, it's something. It's not very it's not super complicated. It depends on a couple of things. First is what tokenizer you are using. Um, so like IDs. So I mean, IDs is not important, but once you get the IDs and you want to go from your IDs, let me bring it here. You want to go from IDs to this embedding layer. So that's one thing that is important because whatever hidden dimension you decide your LLM to work with, this embedding layer would just convert all your IDs into a vector of that length. And then every single layer would just operate at the hidden dimension size. So now based on that, you just need to walk through over all your layers when you are implementing your neural network and figure out the sizes. So that's one of the things that needs to be figured out always. So if you're also interested, I suggest you read the GPT-2 code from OpenAI. So if you go to the source and model, you would see like how these model and encoder decoder are built. So you would see like these are some of the parameters like n embed 768 number of heads num layer. So these are fixed and determined beforehand. And then you would see these MLP layers when they are creating this, they just specify all those shapes. So I'm not going to go over it. Just take a look and you would see like how they specify those dimensions for each layer. I hope it was helpful, but yeah, just post if you have any questions and I'll make sure to answer. So Tanvir, can you please go next?
Hey, thank you, Ali. I love the content and the way, the depth you are going through. I have a quick question. In I think in section 1.2 in data cleaning step, I think you have mentioned there it says 15 trillion tokens, but after like we create, I think you are showing some 200K tokens or something. So I'm just trying to, I got confused with that.
Okay. That's a great question. 15 trillion tokens, right? So let's get first get to the tokenizer part. 15K or 100K. Those are all the unique tokens that we create and inject in the tokenizer. So basically, we have some data, and this data can have a lot of different words, a lot of duplicates, like it could be anything, right? So we train a tokenizer on that tokens, and then we end up with some vocabulary. This vocabulary would have a size of 50,000 or 100,000, right? But when you look at the training data can be a lot more just because there are a lot of duplicates. For example, whatever I mean, a lot of the content has just same tokens are being repeatedly appear in the training data. So that's why it's significantly higher. So if you look at so here, for instance, we have 15 trillion tokens. That means that if we use the fine web and we crawl the web and we just use the fine web to clean it, and we use our tokenizer to tokenize it, we would end up with a very long sequence IDs of 15 trillion tokens. Now, a lot of these tokens are repeated. For example, we have the same words over and over again on internet data. Now, each token is going to be in the range of 0 to vocabulary size. So that's basically it. Santosh, would you go next, please?
Hi, Ali. Again, thank you so much for the depth content, session today. So my question is, so adding the, let's say, like a text and the image or the audio, the video modalities into the mix, especially for the tokenization, which models would work the best? So based on this, I think currently, I mean, today we focused on the text, right? So we like to play around with the image, the audio, video modalities as well.
Sure. I think you are referring to vision language models, right? So that they are trained on both text
Yeah.
tokens as well as visual tokens. So there are a lot of models that are good. Like Qwen3 VL is something came out very recently, and it seems it's awesome. It's open source. It's open weight, and you can just use it here. Yeah, there is a place that says you can how to use it. So Qwen3 VL is awesome, but there are a bunch of other vision language models. I think even the LM Arena, they should have a leaderboard for vision language models. You are able to see the screen, right?
How Gemini
Okay.
1.5 or 2.5 you recommend?
Let's see. So if you go to vision, so here you would see the best models. So some are open source, some are closed. So yeah.
Okay. Yep, sounds good. Thank you, Ali.
Sure. Rahul, please go next.
Hey, Ali, very nice content. Thank you for this. I have a couple of questions. One is in last time you mentioned some of these companies, they do train or post-train the models with the fine tuning. So can you just give us like what does that look like if somewhere were to work on that field? The second one is, can you elaborate on the
Rahul, sorry to interrupt. So regarding your first, just to make sure I understand. So your first question is how companies typically do post-training?
what would be the like work look like if you were to do the post-training? So you have examples there, but I don't think we have had any exercises along on those side. But is there like what's a typical work look like with the fine tuning space?
Sure, I can share some resources for fine tuning, but it's actually very simple. Let me very quickly write a pseudocode. So we have the tokenizer, right? And we have the internet data for training. This is for training, internet data. And we have our model also. We use our Torch NN, build our model or load it, right? Now we want to train it. Basically, the way that we train is first we pass the internet data to the tokenizer. So tokenizer, sorry, I mean, it's just a pseudocode, but just to get an idea. Internet data go to the tokenizer. We get huge IDs. These IDs are IDs equal 15 trillion. Now for batches of the smaller IDs, for batch IDs, right, in IDs. So now we just go over them in a smaller pieces, like every like 1,000 IDs. So it's just a sequence of 1,000 numbers. We pass it to the model. So we do out equal model, which we have. We pass this batch of IDs. So now we have the out. We also know the ground truths. We get the ground truths. We know what is the right next token. We have this out, and then we compute the loss. We basically pass this IDs and ground truths to a loss function, out, and loss, and ground truths to the loss function. And then we use torch dot backward and then optimizer dot step. I'm going to share more, but just wanted to give you the sense. That's it. I mean, it's nothing more. It's just very simple. Most of the problems and complexities are, how to deal with these things at a scale, like making sure that there is no bugs, how to do it at distributed training, some minor things here, different precisions and so on. But at the very high level, that's it. There is nothing more.
But that's for the training data, right? I mean, would you say the same thing for the post-training too?
So both pre-training and SFT are exactly the same. Just the training data is different. Just this is different.
Okay. I think okay. So okay. And then I just have one follow-up question. So when you talk about the batch IDs, like sending some certain data in terms of the batch, can you elaborate what does that mean? I think in your one of your exercises, we had a batch ID set to 1. So would you like logically group certain data set together to process it in a batch, or is it just based on the length of the yeah, I don't know, the maximum context that you want to provide for the models to learn?
So basically, instead of sending examples one by one, we typically batch them for efficiency and also for faster like convergence in learning. So let's say on internet day, we have a bunch of things. Today's podcast is about, and then another one like, let me share the cooking or something like that. So we just batch them, like in this example, 3 examples, we batch them, we send all 3 to the model. So the model simultaneously learned from all these 3.
Okay.
This is basically the batching. It just helps you to converge faster.
Okay, thanks.
Of course. Vaiba, please go next.
Hey, thank you for this wonderful class. So my go straight to the question. So my question is how this embeddings is related to attention mechanism.
You mean the embedding size?
The embedding that we generate, is that the same embedding that we use for RAG after tokenization?
You are referring to
This
this
embedding
inner
layer.
dimension,
This,
right?
Mhm.
So this is basically the same dimension that the attention is going to operate at. So it would just process all of these and make sure some communication happens between all these vectors and just transform each of them.
Got it. So the tokenization, right? After tokenization, it has to be converted into embeddings or just tokenization and directly
Oh, after
inserts
the
as an input?
tokenization, it's a sequence of IDs. It's just a sequence of IDs. It's, for example, here we have 5, 11, 25. This goes to the embedding layer. Now, embedding layer just looks at its own lookup table to go from these IDs to its corresponding vector and just replace them with
Similarity
these.
search. Is that a
It's not
similarity
going to be
search?
similarity search. No, it's just a lookup table.
Right.
It's basically a lookup table that the neural network just keeps track of and update all the weights during training. So row 1 has a vector corresponding to token with ID 0. Row 0. Row 1 has a vector corresponding to a token with ID 1, and so on. And all these weights these are also weights or parameters of this model. They would get updated as we train the model. So these vectors become meaningful. For example, if we pass hi or if we pass hey or hello, all of them would probably end up with vectors that are close by in the embedding space.
I see. And then attention mechanism, right? Can you briefly cover that? How does this attention is materialize? How is that captured?
So basically, attention, it tries to transform each vector by looking at all the other vectors and then see, figure out the similarity and how relevant they are. For example, when it's trying to transform this middle vector, it looks at this vector, it also looks at this vector, and it somehow figures out how relevant each of these two vectors are to this. And then based on that, it would update these vectors so that it also borrows some information from these two vectors. I can also share some resources for attention to better understand that. Nobel?
Hi, Ali. Thank you. Thank you so much for the session. Question on the how do we actually store the corpus when you train a model? For example, when say OpenAI trains their LLM, how do they store the corpus? Is that in files or because it's around 44 TB of data, right, for the initial set of LLMs?
Yes, yes. So they're usually trying a lot of advanced things to store this. I mean, the simplest thing we can do generally is we shard the data into smaller pieces so they become more manageable. And then each of those can be stored with some efficient format, like Parquet or something. And then those can be stored on S3 or some other storages, right? So now during training, then companies typically implement an efficient data pipeline. So basically the data pipeline is responsible for fetch data, read it, prepare the next batches, and make sure it's ready for the next iteration of training. So the data pipeline is just a separate effort, and usually companies have like teams of 10, 20, or even more people working on those, and make sure that at any given time, data pipeline can just go read the files, fetch the next set of batches, and make sure that's ready. So that as soon as the GPUs freeze up from the previous iteration and wants new data to learn from, the data pipeline will just pass it to them.
All right. Thank you.
Sure. Ranganasa, please.
Yeah. Hey, Ali. Yeah. A question on the multi-head concept. Can you explain how does it work? Because I read that it looks at the different aspects of input tokens. And how is it trained? Also, is it like a trained separately? How do you decide on how many heads you need in the model?
Okay, so the training is the same. I mean, we don't have to do anything specific for training. It's just this loop, right? It just takes care of it because part of the model is also all those attention layers, and those parameters get just updated. So that's about the training. We don't need to do anything special when we have attention. About the multi-head aspect of it, even that we don't also need to worry about it because when we create the layer for attention, which is, let's say, inside this model, it would have one additional dimension. So instead of one attention, it performs multiple attentions. And each attention is basically the hope is that each attention head would focus on different things, which we don't know. And we won't know, even at the after training. We don't know really like each head is focusing on what. It's just, but they just figure out. I mean, just the attention just figures out like each head should focus on certain things. So you can just think of it as a multiple, like a set of different attentions, each focusing on different aspects when they are going through this communication between these vectors.
So is the number of heads automatically decided, or is it like a trial and error set by whoever is designing this LLM algorithm?
It is a hyperparameter. So it is a hyperparameter. So let me.
I see. Okay.
So it's, it starts from like 12 or something, and it can go all the way to like to 100, I guess. Let's quickly see if ChatGPT also confirms this. So GPT-3, for instance, had 96 heads. GPT-3 small had 12. So yeah, it's within that range.
Okay. Yeah, I have one more quick question is number of blocks. You mentioned that there are a number of transferable blocks. Again, the question is, how do you determine how many number of blocks you have to stack? And even in the training, do you train with all these blocks in sequence and the back propagation goes all the way back to the embedding, initial embeddings?
So regarding your first question, it is a hyperparameter. So a lot of times when you want to make your models bigger and make it more capable and increase its capacity, it's going to cost more. But if you want to do that, you typically increase all your hyperparameters, right? Including the hidden dimensions, number of heads, and also number of blocks. So if you look at this here, GPT-3, a small, medium, large, XL, and so on, they keep increasing all of these hyperparameters, right? Including the number of layers. And number of layers is what you are referring to. So they start from 12 to train their smallest model, and then 24, 24. And each of these models are trained separately. So basically, they just set the number of layers to 12 when they are creating the model and just train it. So the training, it happens automatically. Again, just the optimizer and backward would just takes care of calculating all the gradients and updating all the parameters of each transformer block.
Okay. Thanks. Thanks, Ali.
Of course. Andrew, please, can you go next?
Thanks, Ali. I appreciate the time. There's also a nice list of questions building up in chat. I had a question that's a little bit.
Sorry, I guess I lost your voice. I am not still hearing. So maybe in the meantime, I'll just take one more question and then come back. Dipanvita?
Hi. Hey, thank you so much for the detailed course. I had a general question which I kind of face at work. So most of the time when we build some models with whatever data company data we have, we never really work on optimizing the tokenizer. It's always about building the model. But what happens in most of the cases, like you pointed out, was we don't end up with a lot of tokens because they are very specific to my work or my domain. So there are various ways to update the tokenizer. We can just add tokens or train the whole tokenizer, but how does that affect, or when we should choose one over the other, and how does that affect the existing tokenization that already is there? How can we maintain that and add more tokens? And I just have one small follow-up, and how does that affect the semantic drift? Like, word can mean something today in the existing tokenizer, and then I add something, it may mean something in my company's domain. So how to do that?
Sure. That's a great question. To be honest, tokenizers, I think, is probably the most boring thing, right? So a lot of times, a lot of companies, they don't really spend much time on figuring out the tokenizer or training their tokenizer, unless they are very big or they are very advanced and they want to do something very new or drastically different in the tokenizer. So a lot of times, what is typical is that we just start from, let's say, the most recent OpenAI's tokenizer, which has like 200K tokens. And that's typically sufficient. I mean, for most use cases, it's sufficient. It has like different languages. It has all these different vocabularies. And it's not also really valuable thing. I mean, so that's why like OpenAI keeps releasing them, right? So it's not something that they want to keep it. I mean, they train something, it works great. They just release it, and then everybody can just start from them. Now, one thing to note is if you have a very, very, very specific and custom question, which let's say the language is, you are inventing a language, it's not even existing on internet, then you need to update your tokenizer. Basically, you need to come up with these new special tokens that you have for your task, and then you basically add those to your tokenizer. And then when you want to train your model, you would end up with some new numbers, right? When you pass it to the tokenizer, because now you are adding new tokens, right, to your vocabulary. So that's possible, and that's also a very innovative way to do it, but it really requires a specific use cases. And actually, Google recently did this. Not recently, but it's generally more recent in the recommendation system. So if you go to the semantic ID, so if you go to this paper, they are trying to continue training an LLM, but then they're also injecting a new vocabulary into it. And those vocabulary are coming from the videos. So I suggest you take a look at this paper. It's going exactly through the same thing that you just mentioned. They come up with the semantic IDs, and then they inject those into the tokenizer, and then they continue training the LLM. And then they show that after this process, they can get better and better video recommendations. So next, Andrew, do you want to go next if your mic is fixed?
Oh, sure. Thank you. I appreciate it. I was going to ask if it's possible to get a different interface on the videos, either embedded on the same platform or embedded from something like YouTube or Vimeo. On mobile devices, it's kind of hard to skip around with the tracking. I also wanted to mention, for anyone who's not watching chat, which is totally reasonable, paying attention to Ali is why we're here, to read the Zoom chat afterwards. It's kind of like an FAQ that's building up. Thanks.
Yep. Thank you so much, Andrew, for the suggestions. Nishit?
Hey, hi, Ali.
Hey.
My first question is like very fundamental, is like with all these explanations, I want to understand how the hallucination happens and what are the like techniques to control it.
So hallucination is a very difficult topic. I mean, over time, like companies like OpenAI, they try to reduce it, but still there is not a very systematic way to fix it. The problem is there is not also a systematic way to understand why it's happening. Very recently, OpenAI shared a paper about hallucination, why language models hallucinate. I strongly encourage you to take a look if you are interested in this topic. But I can give you a summary, like a 2-line summary. Basically, what they found out that the hallucination is because we are not, basically it's because the way that we are evaluating the LLMs. We are penalizing the LLM when they produce something wrong. And then we are not gonna introduce a penalty. So whenever an LLM is not confident about something, it just hallucinates, which is not good. But it hallucinates because during the training process, during the reinforcement learning process, the LLM learned that if it's not confident, it's just better to generate something. And in many cases, it hallucinates. It's like the exam tests. Sometimes if there is no negative point, if you are incorrect, you would just even if you don't know an answer to some exams, you would just make some selections. But if you know that there could be some penalty if you're wrong, then you won't. Now, the current LLMs are based on the former. This study and their paper is saying that the evaluation mechanism has to be different, so that when an LLM is not sure about something, it should not just guess. There would be a penalty if it guesses and it's incorrect. So yeah, if you're interested, just take a. I mean, I really enjoyed when I read this. So yeah.
Yeah, my concern to this, Ali, was like, unless until the hallucination problem is like reduced or solved. So, I mean, I don't think that the systems will be able to trust the LLMs completely. So one thing is like they should, is there any progress being made that, LLMs, while responding, do know that, okay, I do not actually know the response, rather than giving a wrong response, I should rather say that I don't have any knowledge about it, or just stop.
Yeah.
Is there any like progress being made?
Yeah, so there are two levels that this is trying to be solved, right? So one is at the LLM level, not at the system level, which is this paper. Just there are a lot of work that they're trying to just fix the LLM so it doesn't hallucinate. But at the system level, yes, there has been efforts and they've been quite successful. For example, RAG, which is the next topic, right, for this week. Many companies try to just search a web and ground their outputs to reliable facts. So that's one way that they make sure that the models are not hallucinating. The other, which is in our future weeks, is about reasoning and thinking models. They also do the same. So they increase the inference time compute. So the model think, and then it just keep thinking different things and make sure and validate them. And if they're wrong, it goes back to some other directions and think about them and search the web and make sure they're correct. So that's more at the system level. Again, both this week and in the reasoning LLM week, we would see some methods that it would make sure that the LLMs like hallucinate less.
Yeah, thanks, Ali. Just like the next question, that is basically I'm curious about, like processing this trillions or trillion bytes of data to train these models. Like, so yeah, I mean the GPU is like very central to that training. We all know the importance of GPU, that the role that the GPU plays. But is there any like special like frameworks or being on libraries being used, like we used to have this Hadoop and also in the past, and I do know that this Python language, like beyond a point, it's basically it's not that performant. So language wise, there any choices they have, like they go back to like for this performance, they go back to implement something in C or Rust or something like that, if you have any like idea on that.
So just to make sure I understand your question. So your question is, what are some frameworks and tools that allow us in the language model space that allows us to efficiently train at a scale and use distributed training and all those things, right?
Yeah, so the underlying the tech stack in terms of
Yes, tech stack.
yeah, what
Yeah.
is the
Sure. I mean, if it's okay, I can share this because it's more about the links and some resources. I have some good resources in mind. So just ping me in DM or in the chat channel. So I'm going to share some resources for that.
Yeah, that will help, Ali. Thank you.
Sure. Julio?
Yes, thank you very much for your presentation. I was wondering when you mentioned this C4, so the big corpus from the internet. Indeed, the vast majority of the infos are embedded within text, but what about everything related to videos or images? Like how those different type of file are then incorporated within the process of tokenization?
Okay, that's an awesome question. Both for images and videos, we're going to cover them in the last week in detail, including the tokenization. But I can briefly just share what's going to happen. So let's say the input is image or video instead of raw text. Still, it's the same process. We just need to build a different tokenization with a different process to convert the image pixels or video pixels into a sequence of IDs. If you're interested to learn about this ahead of time, you can just search like image tokenizer, or there are a bunch of things. This is the first like VIT paper, but I think you can also read some of these, but basically the key idea of image tokenizers is to go over the pixels and somehow convert them into IDs. And once it's IDs, the rest is the same. The rest is just training a language model. Nothing is different. You just need to replace this tokenizer so it works with images and IDs. Also, this VAE paper, I suggest you take a look. Again, we are going to go over this in the last week, but in case you're interested to learn more, you can go over this paper. They train a quantization process. And then here, basically, they are converting this image into a sequence of IDs, of course, in 2D, but yeah.
All right. Thank you very much.
Sure. Rahul?
Yeah, Ali, I just want to come back to that batch question. So is it fair to assume that one batch usually would or should consist of words that are related to each other? Meaning, based on my understanding, based on one batch would form a context for what we are training for. And based on how the sentence is formed, it will form the based on that context, the next token will be predicted. So based on what's the last token is in that context, based on the positional encoding, it will try to predict the next token. So is it fair to assume while they are training, while the training is being done, that the batch size will have a relative, the context would be for the relative content?
So,
like in this example, like, hi, how are you? If you put everything in the same batch, then model will not be able to accurately predict what should be the
yes,
next logical token.
Yes, yes. So that's why in the first place we are just separating them in a separate dimension, right? We are not just going to pass a very, very huge sentence.
Okay.
So basically, the LLM would process each of these individually, and then the attention happens across each sentence, right?
But
so
is that
yeah.
Yeah, sorry. I was asking, is the hi, how are you? Would that be part of the one batch? And then today podcast is about, that will be a second batch in the training?
So this is one batch, this entire list, right? The LLM would go over this example, converts the tokens into vectors, and the vectors are being transformed. And then based on the output loss, it would come up with some gradients to update the parameters. The same thing would happen simultaneously for this sentence. And the same thing would happen simultaneously for this sentence. And then after all these three sentences, then the gradients would be kind of averaged or accumulated, and then would update all the parameters of the model based on this batch. But none of these examples are supposed to be relevant or semantically related to each other.
Okay, and the way it is being split within that batch is based on where the context, where the context ends, starts and ends, right? Is that based on the codes? So like, hi, how are you will be processed once. Today's podcast is processed in parallel the next, right? So the next token for hi, how are you would be based on the relative meaning of what the hi, how are you is, right? And what's the next best token is.
Exactly, yes.
Okay, I'm just trying to get this in my head, but okay, I think.
Yeah, also feel free to post questions if you have follow-up questions. I can answer them in the chat. Not this chat, the platform chat. Vishnu?
Hi, Ali. My question is, so you mentioned so many decoding strategies, right? Like top K, top P, and all. So how do we know like which strategy to use during runtime, and like how do you decide like what are the right hyperparameters to use? Like, are there any techniques that will determine the success of the generation? Like, what are the success metrics that we generally see to see like this thing, whatever the Gen AI system that you deployed is successful or not?
Okay, that's a great question also. There are some things that we know are not good. For example, we know grid is not good. So you never want to use it in production.
Okay.
We also know that TopP is perhaps the best tool we have so far for generation. There are also some other decodings that are introduced more recently. So one is a speculative decoding by Perplexity. I think it was introduced. But I mean, if you are interested, you can go over this. But basically, TopP is the best. It's just about these parameters, and there is no correct number. I mean, there is no one size fits all. It really depends on the task and also your LLM. So what typically happens in companies that we play with this. We play with this TopP and we play with this temperature. And if especially temperature. I mean, if you want more creativity, you can increase the temperature. If you want more certainty or you want the output to be more deterministic, you decrease the temperature. For example, let's say you want to use an LLM to create some data set or create some captions for images. You want to have a very low temperature because you don't want the model to be creative. You want basically the model to output the most deterministic expected caption for the given image. So this is very empirical. And also OpenAI APIs and all, so they also let you choose when you send your request to choose your temperature or some of those hyperparameters. I think there was a table in the lecture which just sharing some, let's see if I can find it quickly here. So these are just some empirical values. But again, you have to figure out what works best for your use case. But typically in code generation, we don't want creativity or we want more deterministic behavior. So temperature is low. Whereas in creative writing, it can be 0.7 or even more. So yes.
Got it. So on what things they will basically benchmark it? Like, are they going to do some grid search or random search to determine these values on a specific validation data set to come up with these numbers?
Yeah, it's just an inference time thing, right? So it depends on if you have a systematic evaluation in place. For example, in image captioning, if you have ground truths, you can rely on some LLM as a judge systems to come up with the quality of your output. Then you can try different values, run evaluation, get the numbers, and see which pair of value or which temperature basically is giving you the best numbers. Otherwise, other than that, if you don't have an evaluation, like a systematic evaluation mechanism, you can it's typical just to eyeball and see, which of these are producing something better and then just stick to those.
Thanks, sir.
Yeah, no worries. Tanvir?
Hey, thank you, Ali, and thanks for all your patience in answering these questions.
Yep.
Quick question. I think when you were responding to someone, maybe I misheard that we can train the tokenizer. I thought like tokenizer is basically the vocabulary, right? Or can we also train the tokenizer?
It's just a terminology. I mean, in many cases online, you may see that they are referring to it as training, but basically this whole training, what it means is that they go over the corpus and then they create the vocabulary. That's it. What they mean by training.
Okay, I have just one follow-up question.
Go ahead.
Regarding, I mean, when we like you had mentioned that, hey, like we need to pass the neuron layer. It can take only numbers, not the text. So that's why we have the tokenizer, which converts it to numbers. But what's the purpose of? I'm not able to understand. What's the purpose of embedding layer? What does it do? Like we already have the numbers, we can feed into the neuron layer. Then what's the purpose of embedding layer and then it converts to vector?
Yep, excellent question. Let me okay. Let me now zoom out. Over here, it's just easier if I go over these visuals. Okay, so the reason that we have this embedding layer is because if we don't have it and we just use these numbers are not meaningful, right? Like, how are we getting these numbers? We are just looking at the index of the word in the vocabulary, right? So hi can be indexed 10, and then hello can be indexed like 2000, right? Although these two words are very similar. but their IDs are very, very different. So the neural network would have a very difficult time to figure out all these things and learn about the meaning, like the semantic meanings. The reason that we go from these just numbers, they're just random numbers, right? The reason we go from these random numbers to these vectors is that we want to, over the course of the training, we want to update these parameters such that now each token has a vector which is meaningful if we visualize them in the embedding space. So then in that embedding space, hi and hello would end up nearby. So this can be very, very important and powerful for this transformer, because if you replace this hi with how, the embedding would be very similar, and then the output is going to be likely very similar. But if you just pass these numbers, if you replace hi with how, suddenly instead of 10, then transformer would see 2000, and they are no way related to each other. So that's the main reason that we use this embedding layer. Shashank?
Yeah, thanks, Ali. I have maybe an extension to this question. Like when it comes to self-attention, one piece of puzzle which is not clear to me is how the weights for the Q, K, and V metrics are derived.
They're just being updated by the like through the backpropagation mechanism, right? So basically, initially there's just some random weights. You pass some inputs. Based on the inputs, the neural network generates some probabilities. Then from the probability, we compare it with the ground truth. We come up with some loss function, right? Some loss function here, and
So
then
is it while training the model, the Q, K, and like the V metric specifically, right? Matrices, those get updated because they
yes.
basically tell the meaning, right? Like how the relationship between, like, you know, the words basically, right? And from different aspects. So, I mean, the embeddings are derived at a time of training the model, but in order to derive those matrices, like, you know, the embeddings are multiplied by the weights for QKV, right? So
so not
the weights are also derived at that time. I'm a little confused, like, you know, how they will add the different aspects at the time of training.
So that's the whole thing, right? So it's not really, we cannot really interpret the process. What's going to happen is that all these layers, like embedding layer has some parameters. It's just stored in a weight matrix. Attention has some parameters, KQ value, stored in some matrices, right? Feed forward, the same. So initially, when we start this model, when we build this model, there are just a bunch of parameters, and they're random numbers. Now, when we start training, based on the loss function, we backpropagate, meaning that we calculate the gradients for all the parameters. And then for each parameter, we try to tune it a little bit such that for the same input, next time, the final output becomes more accurate. So during this process, all the parameters, including key values and every parameter in attention and feed forward would get updated. So was that helpful?
Yeah, I mean, somewhat. But is there a like, you know, material or something that you could share, like just to go one level deeper and understand like how the weights are that one piece is not very clear to me basically. The rest of the process, I think I've got it.
Sure. Yes. Please just send the post and then I'll share resources.
Sounds good. Thank you.
Cassie?
Hey Hari, first thank you so much for this course. It was an eye opener. I don't know, like I could have learned so much within 1 week, and your patience in taking up questions and answering, that was awesome. Answer every question. So I have some one idea, one thought in my mind. I don't know if I'm asking the right question, but normally when we did encoding, decoding on a one model, on one base model, basically we used, and then when we try to switch to a different model, the tokens change basically, if I'm not wrong. They may not be the same, but they may change.
Yes. When we switch to a different model, it depends on what tokenizer it was used to train that model. But in many cases, if the tokenizer is not the same, so what that means is that for the exact same input, you would get a different sequence of IDs.
Understood. So basically, when we work on, we have to stick to a model where we are working on. Tomorrow we change the model, our whole logic patterns changes out. So is it possible to use like multi-models somewhere down the line to see derive best out of it, or it's too complicated to think about it?
So I mean, even if you want to use multimodal, I mean, we would see some examples in the last week. Even if you want to use that, you still need to make sure that you use the same tokenizers. So that's why here, for example, in Generate, right, we make sure to get the models and its corresponding tokenizers at the same time. If you just switch the tokenizer to the different tokenizer, the model would not be able to accurately predict next tokens.
Understood.
Prasad, please go next. Prasad?
Oh, okay. Sorry, I was in mute. So you explained the embedding models, that is text or sentence embedding models. I have a question on follow up that, but if you have any documents, I will go through and try to understand. The question is, I understood the embeddings which decides what or give the context of LLM, what is retrieved before the generation, right? So what quality it is, how it is grounding. The grounding truth depends on the quality of a reference or the text given to. So the quality of text given to LLM depends on how the text is embedded and um, transformed, and the similarity is measured between the chunks or
Yeah,
what are
so, so sure. Regarding the grounding, right? So that's the main focus of RAGs, right? And Week 2. So we can perhaps cover those more in next project. So that's for grounding. But also, I mean, even for grounding, we would use this embedding layer is still important. I mean, once after training, once we have a good embedding layer, so it would guarantee us that we go to almost similar vectors for similar words, right? So,
Yeah.
and that's going to be
Question is-
useful for grounding. So whenever we have external information, we can also use the embedding layer to convert them, let's say, into vectors and then run some nearest neighbors. I mean, if you go over, if you get a chance and go over the guided learning of Week 2, we talk about this.
Sure, sure. So the only concern here is, so how to choose this, maybe if you cover, fine, how to choose this embedding models for um, particular use case, because data is a domain specific or the region specific. So how?
So this is just to clarify, this is not an embedding model. So we have also a concept of embedding models, right? So those are models that are specifically trained to be used as an embedding model. So for different use cases, this is an embedding layer, and a lot of times this layer is trained along with the rest of the transformer. So if you load any LLM and inspect it, like all the layers, you would see an embedding layer. So what that means is that basically all of these are being trained at the same time. This is different from embedding models. We have some examples of actually embedding models in project 2, I believe. But again, if I mean, you can just search embedding models, and then OpenAI and some other companies, they do have their own embedding models. And also there is a leaderboard of that. So it's just an entire model being trained just to embed. Basically, just you pass some sentence or anything, it would just return you a list of numbers.
Oh, makes sense. I did confuse it, looks like. Okay, fine. I understood.
Okay, great. Prashant?
Thanks for your session. I was with you and writing on my code until 2.1 section, and then I felt like it went a little bit ahead, and I could not cope up with the pace of the course. I mean, I will take time to go over after this. The question is, like, I'm coming from finance and banking domain. I'm still not able to connect dots, like whatever I'm learning, how I'm going to apply to my domain as such. So for example, in the diagram where we have this embedded layer where the inputs are being passed, for example, if I have the time series of Apple and Google, and I want to predict next 5 days of prices, right? What will be the input they have to give from the finance perspective, so that the generated output will be one vector with the next 5 days price?
Mm-hmm. So I cannot have a definite answer for this. There are different ways, and I'm sure there are lots of papers around it. Typically, a very good baseline or a straightforward solution for this type of thing is just to convert everything into a text-to-text setup. So basically, when you have just a sequence of prices, you can just train a transformer or an LLM. You pass this sequence along with all other events and metadata that you want to consider during training. And then the output is going to be the next price, like the price for the next day or something like that, depending on what your granularity is. I really cannot comment more because there are lots of different ways, but I suggest you take a look at this paper. It's a T5 paper. It's not related to finance, but basically they are using a transformer and they are using it for different tasks. And they convert everything to text input, text output, like a translation, sentiment, and everything. So you may find it, you may get some ideas if you go over this.
Okay, thanks, Ali.
So it's called T5 paper. Yeah, sure.
Okay, if you can put on chat, or should I have to?
I mean, it's going to be in the recording.
Oh yeah. Okay.
If
I'll
you
click on
don't
it.
find it, just post in the channel. I would share it with you.
Sure. Thanks, Ali. And just one comment, Ali, before I go. Any suggestion, like for the project 2, right? Do I have to do preparation before I come to the cohort? Or this time I thought like I'll go with your pace and learn side by side, right? Is there any preparation that I have to do before I go for project 2? Because this project I could not cope up with the pace.
Okay, so yes, I have some thoughts here. So for the project 2, first I would strongly suggest to go over the guided learning because that will set up a lot of the foundations and concepts. Project 2, I also tried to improve it based on all the feedback. So now it comes with a lot of links that you can go and look at the documentations. So that's one thing that I expected it would be probably easier to follow and more intuitive. And second is that project 2 is also providing you like a step-by-step, like very clear like steps to implement.
Okay.
And the third thing is that it's more abstract. So I think so from this project forward, project 2 forward, things gonna be more at the application level and more abstract. So all basically a typical process would be you want to, let's say, load PDFs, you search the web, you see which libraries do provide like that functionality. You read the documentation. It's going to be typically 1 or 2 lines of code. You just copy paste or you just write it to load your PDFs, and then that's it. So yes, starting from project 2, perhaps things would be more like abstract, like higher level, just using some tools or libraries to load things and just connect things together. We start relying on LangChain and their functionalities. So yeah, and still, if you have questions, feel free to post them in the channel. But I think if you first start with guided learning and then you just follow the project and all the links provided, it should be intuitive.
Okay. Thank you, Ali.
Banu?
Hey Ali, quick few questions. How much of what we learned as a programmer in this week 1 could I reapply to uh, building an LLM, other kinds of LLMs? Like right now, we have seen a text generation model. If I were to do text to speech, speech to text, let's say document intelligence, or if I'm using anything other than GPT-2, how much of what I've learned in week 1 would I be able to reapply? Or what sort of changes that we could expect when building other kinds of models with respect to at least building an LLM?
Yeah, that's an awesome question. So basically, the sequence of chapters we have in the cohort, like the sequence of topics we have in the cohort, basically it tries to gradually build on top of the previous guided learnings. So for example,
Okay.
in RAGs, we learn about other more advanced models and load them. And then we see more like different things in the coding as well. By the end, perhaps we should be able to build something like very, very simplified version of like a multimodal agent kind of a thing. So we load some reasoning model, we have some RAG-based setup, we have image generation, video generation, and the chatbot. So we can just type something and then it would answer. But a lot of things are going to be helpful if you want to switch to other things also, right? So for example, I mean, once you learn how these things work, you can just switch to best, like most state-of-the-art models and just play around with them, whether it's LLM or whether it's a reasoning model, right? Once you learn about the RAG and like a simple embedding model setup, you can just switch to the best embedding model out there and connect them. And then suddenly you would go from a very simple prototype to something a lot more stronger based on the best models out there. So yeah, the hope is to just build gradually on top of each week, on top of the previous week. Peter?
Yes. Thank you again. I just want to make sure if I understand something correctly, and then I have a follow-up. LLM stack, if you want to call it that, it has a tokenizer, an embedding layer, and then the hidden layers where all this stuff happens in the box above. A tokenizer is fixed for a given model. You can't just use any tokenizer with any model because all the training is built around those token IDs that get generated. And then same thing with embedding layer, right? The vector output from embedding is fixed after you start training, right?
Yes.
Thank you. And then if you can, going back to the question I asked initially, can you summarize your intention in including this content? I mean this in an honest way. Just I'm interested in what principles you are trying to emphasize in this first week, if you can share.
Yep. So first week is more focused on the foundations and like learning whatever is necessary to know like how like simpler versions of ChatGPT work and how they can be really built or at least used in terms of coding. And it's basically the necessary knowledge for future weeks. A lot of things like around RAG. RAG is basically has two parts, right? One part is retrieval, and then the other part is generation. And generation is entirely relies on the LLM. And so that's why like week one is just about LLMs, how they are trained, what are all the different pieces, how they actually generate text token by token, so that when we switch to RAG, we don't have to worry about the generation part, right? So then we can focus on the retrieval part only. And then the third week is, let's say, agents, right? Now for agents, still LLM is one piece of it, but it's a very small piece of it. There is just now new concepts like function calling, MCP, all those things. And also the multi-step agent. So there is this loop that is being introduced. So basically the whole design was based on the fact that first we understand the foundations and then slowly we build on top of each week. And then, at the very end, we would, the hope was to cover the most, important topics or concepts in AI engineering, or relevant in AI engineering. And also we get a sense of all the popular features out there, like how they're built, like reasoning models or a feature like deep research, right, by Anthropic or OpenAI or even Google that they're providing, image generation or video generation, how these things are happening, and also the multimodal agent. So that's how this is how the thinking process was for coming up with this sequence of topics. I hope it clarifies a bit. Great. Tanvir?
Thank you, Ali, once again. So quickly, the picture you are showing here, so is it correct to say that an LLM consists of tokenizer, embedding layer and this transformer?
Sorry, can you repeat your question again? An LLM consists of
And
LLM.
is this whole thing is LLM? Is it correct to say?
Oh,
Tokenization.
I don't have a good answer for it. I mean, you would see different terminologies if you go online. But basically, the LLM at the very core is the transformer. And transformer, it means basically the embedding layer and the transformer blocks and the linear layer. Even tokenization is not considered part of the transformer model. So, but again, there are different terminologies. Different people have different levels of granularity when thinking about this. But I would say perhaps the LLM can be think of the embedding layer and the transformer blocks, and of course the linear, like anything with a parameter.
Okay, got it. And I have two more quick questions. So one, the exercise you did, the notebook with the code, how soon that can be available?
Not too long. I mean, I'll just try to clean it up, and then I would push it in the repo.
And in the repo. Okay, that's good. Yeah. Thank you. And last question, this parameter and hyperparameter, can you expand a little bit? I'm trying to wrap my head around. Thank you.
Parameters are the model's parameters. So they would be learned. You are not gonna touch them. You basically let the training process, they would be updated until you come up with some optimal set of parameters. So these are things that would be automatically updated during the training. Hyperparameters are not really trainable. You just set them to some fixed values. For example, you set the hidden dimension here to 4. It's going to remain 4 for the entire training process or the number of blocks. So yeah, that's basically the difference of hyperparameter and parameters. They're just the naming might be a little bit confusing, but parameters is just anything about the model that is going to be learned during the training process.
Thank you.
So, all right, so I guess we'll have to end soon. So I'll take the 3 remaining questions and then we can end. Rajesh?
Yeah, thank you so much. I appreciate it. Won't take so much of time. I had put in your private chat. So there is this LLM's output. There's a section that is pasted, passing a token sequence through LLM yields. This is in the solution notebook in 2.4. Yeah. So I'm trying to get some intuition that the first section, first text that you have put in, which is a token of just above the code. Yeah.
Can you repeat the last part of your question? So the text is here, and then I didn't get them.
No. The text or the words written above the code, right? So the sentences written above the code. If you scroll up, that's so. I wanted to get that intuition on passing a token sequence through LLMs. See the primitives of tensor, logits, and the shape of it. That's number one. I wanted to get some thoughts on how to interpret that. Tensor being a multidimensional array, logits being what is being predicted, and shape that size sequence. I didn't understand, what those
right.
And then also some information on what softmax. Yeah.
What softmax? Okay. So batch size, sequence length, vocab size. This is what you want clarity.
Yeah.
So if you think of this output, what is the shape? So we have sequence length. We have 3, and then we have hidden dimension. Now, when we apply linear, we are going to apply the linear. I mean, in the code. In the code, we are applying linear on all of these and then discarding the rest. So that's a minor detail. But let's say after you apply this linear, you are mapping the dimension to the vocabulary size, right? Because you want to treat those as the probabilities associated to each token, right? So if you see the output of the linear, we would still have, if I do something like this, right? And we pass all these 3 to linear. The output would be sequence length times vocabulary size. Now, this is one example. In practice, we send multiple examples in each round. And that's what batch size refers to. So in each round of training, we don't send one example. We send like 10 examples or 1,000 examples. And each examples is being processed simultaneously and independently.
Got it.
So that's where this comes from. And softmax. Softmax, we apply it because if you don't apply softmax, these are going to be just numbers, negative numbers, positive numbers. You cannot really treat them as probability. So softmax is a function which is just doing that. You pass a bunch of numbers, it just exponentiate them, and then make sure that they sum up to 1. So this way, since it ensures that everything is positive and sums up to 1, you can treat them as probabilities.
Okay. So completely unrelated question on use cases. So given that this is already probabilistic, right? So I could see the use cases being used in chatbots and coming up with responses, because enterprises, typically we build systems based on deterministic outcomes. So what are the use cases that people use this in other than, language interpretation, chatbots, etc.?
So we would see a lot of we would see a lot of use cases. I mean, for example, in week 2, the main project is like building a specialized like a chatbot, for instance. So we start from some LLM and we try to customize it to a chatbot for some imaginary like retail store, something like that. So I can also share more if I can think of more use cases. I can definitely share more in the channel. Sonia?
Yes, yes. Hi, Ali. So just a request that when you push it, you just said you're going to push it to GitHub. Could you push it in a way that we can open it in Git collab? Because I don't have my local setup yet.
Oh yeah, of course. I mean, it's still the same thing works. I'm gonna push it. You can just open it in Google Colab and just run it.
Yeah, and somebody gave, we have one error happening, right? So somebody gave a script. So did you're going to review it before we use it so that, that error in when we open it in GitHub, after we push it, we are on some of cells, we are getting an error. Few people reported it. So will you review that script and then we can use it? I mean, I didn't try it yet.
Yeah, I think the same day, like the same day it was fixed. I mean, try it. If it doesn't work, just let me know. But it should be fixed.
No, it is like when we push this code, Google Colab to GitHub, and we open it, there is some.
That one.
Yeah,
Yeah.
That
Yeah,
error.
I can. Yeah, I can look into it. I have to see. I mean, so when you want to push the code in your own Git, you face that error. I can look into it and see what the issue is.
Yeah. It's like once I push it and on GitHub, and then I try to open it, it says there is some rendering error that it doesn't. Like it's for tick token. It's for tick token one, I know, and it's for two of them. I faced that issue. So then somebody posted that they use this script. So I didn't. So if you can look at it.
But maybe you can also try the same script because it may work. I mean, if it's shared, because basically this is something that is happening on when you want to push on your own Git repo, right? So this is not something that I can push to the main Git repo. So I would suggest try that. If you still face the issue, just post or DM me, and then we will figure it out together.
Okay. All right. And just one thing, please, if you can make sure that everybody is muted during the lecture, because I think I was hearing some background sound while you were giving the training today.
Sure. I think everyone was muted by default, but sure.
I looked up and I kind of saw like 4 or 5 people. So I don't know, some little sound. It was a little disturbing. So appreciate it. And like one guy said, who was from finance background, he was saying that, oh, he lost you. I also I did the whole thing by myself. But I just wanted to share that, okay, I lost you after some time, and I'll now go through the code that you will give and all your explanation to understand better. So
sure, yeah. Thanks. Yeah, sure. Thanks for the feedback.
Sure. Thank you.
I mean, from when I started copying the code, basically the purpose was to not repeat basically the same thing. So I think if you watch the recording, it should become more intuitive. That was the case. So a lot of the code that was pasted are basically the exact same like for loops to load the model and tokenizer from the previous cells that we already discussed. But yeah, thanks for letting me know. I try to make sure that it's going to be more
yeah
intuitive.
even like see, everybody's at a different level, so I'm sure, so like when you explain it, it really adds like to me it really adds a lot of value. Like somebody was asking, and recently somebody asked, and then you explained that, oh, that linear is over there and batch is over there, so I could not earlier make the connection that all that batch and sequence length is that thing. But now during the question, when somebody asked and then you pointed to the diagram, then I could connect that, oh, it's that same thing. So it's just
Yeah.
like because I
Yeah,
mean,
no,
yeah,
that's
like,
awesome, and that's awesome, and that's great to hear that. So I think that's one of the main values of the question answering. So I think there's some questions, and then it would help to clarify more. I'll also try to make things as clear as possible in the project, but still, I'm sure that there would be a lot of questions that would also add value to everyone else. So, but great to hear that.
okay, thank you. And you will make some announcement